Okay, so today we are starting with deterministic signal modeling. Deterministic signal modeling, and almost all of this discussion is from Hayes's textbook. Okay. So what we have said previously, let's remind ourselves. We had stochastic signal modeling. So what was that? Stochastic signal modeling. So let's assume that we have in our hand a measured power spectral density. Okay? A measured power spectral density. Now let's call that process X, and its power spectral density is given to us, it's a measurement as px e to the j omega. Now the question is, how can I realize this process? Okay, so this is a valid power spectral density. Is there a way of generating this process? So stochastic signal modeling. So I'm trying to model this process by, as you see, I have white noise input and I have an LTI filter. Now the question is, what is this h of c? Find h of c to realize or synthesize the random process x of n with power spectral density px e to the j omega. Okay. This was the thing that we have studied previously, and we have studied the cases of, all pole, all zero, poles and zero cases for this filter. And we have even studied the spectral factorization. Okay. So when this one, this given measurement, power spectral density factorizes, so let's say that it's the ratio of two polynomials in Z, we have seen that it's possible to apply the spectral factorization idea, and with that one we can find h of c also. Okay, many other topics. So today's topic is a related topic, but as you can imagine, this is distinct. So because this is deterministic signal modeling. So let me say today, so we are starting with, given a sequence x of n, which is for n greater than 0, and x of n is assumed to be equal to 0 for negative n. Okay. So we are given that sequence. So you may consider this, maybe this is like a measured impulse response. Okay. So measured impulse response of a causal system. Now the question is, can you characterize this impulse response? So can you model this impulse response, with a filter? Okay. That is our next task. So what is h of c over here? H of c is, let me see, what is our notation? H of c is, so I have b0 plus, no, this is not b0, bq0 plus bq1 z inverse plus bq of q. Is this the case? This is capital Q, I guess, for visibility. Z to the minus q divided by 1 plus AP of 1 Z inverse goes like this up to AP of P Z to the minus P. So our task is, finding or setting these coefficients on the numerator and the denominator of this ratio such that, this impulse response h of c approximates this measured impulse response. Okay. So how can I do this? That will be our next task. As you see, this is quite similar to this one, but different, obviously. Okay. So let me see. Let me start with this example for the illustration. Let's say that my h of z is b0, 1 minus a1 z inverse. Okay. So here I have q is equal to 1. Okay. And q is equal to 0. P is equal to 1, because as you see, I have a 0th degree polynomial on the numerator, and I have first degree polynomial in Z inverse on the denominator. So I have a total of Q plus P plus 1, which is equal to, well, 2 degrees of freedom. 2 degrees of freedom. What do I mean? I need to set this A1 and I need to set this B0. Okay. So in general, you can see that we have P plus Q plus 1 unknowns in this problem. Okay. So what is the impulse response? Now, the impulse response. So this is a model actually. I am trying to set the parameters of the model. So the impulse response, again, I am considering on the causal cases all the time. You know, causality is always assumed in these calculations because it's like a practical problem. Okay, I am with the causality assumption, let's say. So this is equal to b0 a1 to the power n u of n. Okay. So this is the case. Now what can I do with this one? So this is my impulse response. So how can I make this impulse response by selecting these two parameters, b0 and a, similar to or equal to this x of n? I would like to equate it if possible. So one way of doing it is, well, you can say that let's equate first, again, P plus Q plus 1 samples of x of n to h of n. Okay. Then, if this is the idea, then you can say that h0 is equal to, over here, b0, h1 is equal to b0 times a1. Then you say that, okay, then let me equate this to given measurement. What's my measurement? My measurement is, so here's a problem. So I'm only using first two samples of my measurement, but you know, this is an approach. Okay. So you see that by equating these two equations, the left-hand sides to the measurements, I get b0, and from this I get a1 also. Okay. But you can sense a problem because this measurement is given for all non-negative indices, but I'm using only two of these. But you know, as I have said, this is just a method. Okay. So let me have a second example. Well, if I have h of c, b0 plus b1, z inverse, 1 minus a1, z inverse, okay. Then let's apply the same idea. So if I have this inverse z transform application to this, well, this part is as before, as you see, okay? So this is equal to b0, a1n, un. And this part is nothing but shifted version of this one, I should say this one, and multiplied by b1. So this is b1, a1, n minus 1, un minus 1. Okay? That is it. So I have, this is my model with this time 3 parameters. So I'm trying to set these 3 parameters. So one thing that we see is, actually we end up with nonlinear equations, isn't it? Well, let me do this. Now again, let's do this idea. h0 is equal to b0. Okay. h1 is equal to b0 times a1. Well, okay. h1 is equal to b0 times a1 times b1, plus b1, sorry. Okay, because this one also appears. h2 is equal to b0 a1 squared plus b1 a1. Am I right? N is equal to 2. Or this is like a geometric series, okay? So this is geometric. This is also the late version of the same series with a different coefficient B1. Is this correct? Okay. Now again, this time, okay, this is a richer model, meaning that it has more parameters. So let me equate this to x0. Let me equate this to x1, my measurement. Let me equate this to x2, and we are done. But what we see is, no surprises, we have a nonlinear equation system. Well, the obvious reason is, these are the coefficients. The unknowns are the coefficients of this denominator polynomial. And similarly, we have numerator polynomial. And the pole zero locations of this transfer function is affecting the impulse response. And so I need a mapping from these coefficients to poles and zeros, and they will be even multiplied because of this partial fraction expansion. So you see that there are several nonlinearities involved. Okay? But this is just a method. Is it easy to solve? Not very difficult to solve, as you see. So maybe it's more difficult than this one, but I can give it a try if I wish. So instead of doing such things, but this will be our task, we will be first applying a method called Pade's method, or Pade approximation, for the solution of the same problem. Okay? And this is very practical, and it is used very widely in many numerical applications, let's say textbooks, in many numerical results, and so on. Because, again, as I have said, this is just an approximation method. So what is Pade's approximation? Pade's approximation. Okay. So let me write this. H of C is BQ of C divided by AP of C. But let me define BQ as summation. This is K0 to this, BQ of K, Z to the power minus K, okay. And I have 1 plus, this is K from 1 to P, AP of K, Z to the minus K, okay. So this is our model for the system, and again you see the parameters of this model. Now what is the task? The task is, well, I would like to equate this, if possible, this H of C, to X of C, and I write, okay, if possible. And if possible, I would like to equate it for all n. In other words, sorry, not n. So there's a polynomial on the left side, there's a polynomial on the right side, let's say. I would like to equate all powers of those polynomials. Not only the first three, first up to the second power and so on. Okay? So how can I do this? So let's assume it's possible to equate this. Okay? Then you have the following. Then on the left side, you have X of C times AP of C is equal to BQ of C. Am I right? If it is possible to equate this. Actually, this is a great step because I know this polynomial. This is something that I don't know. This is something that I don't know. But you see that this, this part and this part is separated. B's and A's are separated right now. Okay, if it is possible to do this. Okay, now if I take inverse C transform, what do I know? So this is my X of n sequence. Let's remember, X of n is, usually, it's all 0 before n is equal to 0, and it has many legs. So up to infinity, okay? X of n is our measurement, something like this, okay? So this is X of n, a given sequence, convolution with, well, this AP of C, AP of n, okay? And this is BQ of n. Am I right? So I am at that structure. If equality exists, then there is this equality in time domain, and so on. Okay, let me erase this part. Let me try to write that convolution relation over here. Let me see. Let's have something like, well, this. And so on. Okay, so what is this? X of n convolved with unknown sequence A. Let me write a few lines of this first. Okay, so what's going on? So at the end of this convolution, what do I have? So let's see. X of n is a sequence defined for, it's a causal sequence for n is equal to 0 up to infinity. And it's all 0 for negative indices. AP of n is exactly like that. Its zeroth leg is 1, and it has p other legs with unknown coefficients AP. So its zeroth leg is 1. So I'm taking the convolution of this x with this, as you see, A sequence. Okay. What about this one? This one is also in the same form. So it has B0, z to the power 0, which is this. B0, z to the power. I have BQ1, etc. up to BQQ. Now you can say that if I evaluate that convolution and check the result at n is equal to 1, n is equal to, let's say, 1. Or this n is equal to 0. Okay. What do I have? Well, you have x of n convolved with, this is nothing but 1, AP of 1, delta n minus 1, AP of p, delta n minus p, and so on. Let's forget about the right-hand side. So I'm taking the convolution of, I'm calculating the convolution of x of n with this. Okay. So how do you do this convolution? Well, very easy. Convolution is distributive over this addition operation. So this is x of n times 1 and x n minus 1, shifted version of x, times AP minus 1. Okay. So index n is equal to 1, index n q is equal to this. So please see this axis as n axis, okay? Like this axis, n axis. Now you see this x of n sequence listed over here. This sequence is multiplied, first column is multiplied by 1. Then second column is multiplied by AP1, but what is the difference between the first column and the second column? Second column is one sample shifted version of the first column. Okay, so actually this is nothing but the implementation of convolution's first two terms, x of n plus AP1 times xn minus 1. Okay, it goes like this. For the AP2, let me include that. Okay, as you see, for that one, it's 2 shifted by 2 original sequence, and you are multiplying by AP2 and doing this calculation. Or do this one, for example, n is equal to 2. So how do you do the convolution? x2, this is input at time 2, times this response, xn, times, this is the previous response, x0, times the previous 2, okay? So this is the way you calculate the convolution. Like at the output n is equal to 2, I have nothing but the linear combination of previous, let's say 3 samples up to time n is equal to 3 with the weights this one. And this is how we calculate the convolution, isn't it? In different ways. So this is called the convolution matrix. Again, we have discussed this a little bit before, but right now we are being introduced to it in more depth. Okay, convolution matrix. And if I have an equality like this, as you see, I have a matrix equality, matrix vector equality, like this one. Okay, so those two things are the same. Now what is interesting is as follows. In Pade's method, Pade observes the following. Now n is equal to q plus 1, and it goes up to n is equal to n, up to infinity. Pade says the following. Pade observes that the bottom part of this matrix, the bottom part of the matrix equation. So let me mark this with some other color, let's say with red, below this red line, okay? So I'm talking about these equations, okay? Bottom part of the matrix equation below red dotted line, which is this kind of thing, red dotted line, contains only APK as unknown. Okay? Because as you see, B's vanish after this first Q equations, or Q plus 1, because it starts from 0. Okay? But this part, this bottom part, contains only, right hand side is equal to 0, so it's only a function of x and a. Okay? So that is it. Then Pade uses the first, let's say P, I have P unknowns over here, P equations. Let me erase this because it's exactly that. P equations of the bottom part of the matrix to solve for AP of case. Okay. So how is this possible? Well, Pade does the following actually. Writes an n AP1 AP of P. Okay, so the first column is multiplied by 1. Okay, this one. So you move it to the other side with a minus sign over here. X Q plus 1. And you have P equations like that. Then AP1 is multiplying XQ. Okay. This is Q minus 1. X Q minus P. This is Q minus P plus 1, sorry. Let me one more x Q plus 1. And this is P minus 1. Okay, x of Q. Okay, so I have such an equation system. So let's check this, whether this makes sense. So I'm subtracting plus 2. Okay. I get something like that. Okay, so this equation system. So in the bottom part, what do I have? I have this coefficient 1. 1 is multiplying this first column, and the other coefficients are multiplying the rest of the columns. Then you move the first column of this matrix to the right-hand side, as you see. But don't forget, there's a minus sign because of this moving to the right-hand side. Then you get a, what do you have? You have a P by P matrix over here. You have a P by 1 vector over here. You have a P by 1 vector over here. You solve for A's. Of course, you assume that this matrix is invertible. Then, after finding A's, let me see, a P of K's, insert in the top part to find, well, this B's, EQ of K's. So once this is known, you don't have this. Okay, then you insert it over here, then you evaluate this product, then it becomes your B, unknown B's, BQ case. Okay, so Pade's method is extremely easy, as you see, and there is no nonlinear equation solving, etc. So the critical step is, well, previously we were equating h of z to x of z, but right now we are not doing that. We are equating x of z times AP of z is equal to the BQ of C. Okay, we have this equality instead of this original one. So this is the reason that B's and A's do not interact with each other, well, at least for this bottom part of this matrix. And Pade is making use of that observation. Okay, now you can criticize Pade's methods. You can again say that, okay, let me erase this. You can say that Pade's method has, a strong, let's say, problem, a big problem. Pade's method uses only, let's say, P plus Q plus 1. As you see, Pade's method is again only using P plus Q plus 1 samples of x of n to set the parameters, but ignores all other x of n samples. Okay, so this is a criticism, because for the Pade's method, what you need is only up to this sample, okay, or x q plus 1. Q plus P plus 1, because all other samples after that one, they are not used in this equation system. Okay, so this is a drawback, you may say. I'm not using the full information. So what can we do? But maybe before that, let me have, so there will be solution by Prony, but let me have a, example with Pade, H of C. Okay, so over here I see that I have two poles, number of zeros is equal to 0, so I have, as you see, 3 degrees of freedom. Okay, now let me write this matrix. That is it. B0, that is just B0, 0, 0. So this is X0, X1, X2, So it's x0. I have such an equation system. So I'm writing only this part of this, 3 by 3 part of this, because I have a 3-element vector over here. Okay. So it is this part of this matrix, and it is this part of this equation system. So that is it. So what is the solution of this? Well, the solution is, if you move this to the other side, AP of 1 is minus x1 over x0. Okay. AP of 2 is, let me write this, minus x2 plus x0 divided by something like that, x0. This is correct. So this is, x2 is on the other side. x1, AP of 1. Okay, that is this one. Okay, divided by x0. And b0 is equal to, first line, is equal to x0. Okay? So as I have said, if you apply Pade's method and you are trying to fit 2 poles and no zeros to this measured sequence, you are only using up to elements x0, x1, x2. You are not even using x3. Okay? So that is the criticism that we have mentioned over here. Okay? Now, but at least this is a very feasible and easy method. And if this method works well enough, that means that your problem is solved. Okay? But if it doesn't work, then what else can you do? Okay? So this is an approach, as I have said. So what else? So this is Prony's extension. This is called Prony's method. So Prony uses the bottom part of this matrix, bottom part of the same matrix, but applies a least square solution to the bottom part of the matrix equation system. Is this clear? So Pade was using up to, let's say, some part of this, up to xq plus p over here. Okay? But there's x of n below. There are so many other equations below that one, let's say. So Prony, again, uses this part of this matrix, but sets a's such that the least square error is minimized. Okay? That is the Prony's method. So if I write this, so how can I write this one? Just to clarify this. So let me give a name to this bottom part. So let me call this part as, this is my X matrix, and its bottom part is BOT, let's say. Okay? So I have an equation system like that. X matrix, BOT. 1, I have this unknown vector AP is equal to all zeros, 0 vector. Okay? So let me write over here. So this is X bottom part, let's say 1, first column. So this is the rest of the columns, let's say. X bottom part, rest. Let me write it like this, rest of the columns. Times 1 AP vector is equal to 0 vector. Okay? Then, let me go this way. X bottom part of this rest of this matrix times AP unknown vector is equal to X bottom part of this first column. So this is first column of X bottom, and this is the rest of the columns. Second and, let's say, up to pth column. Second and all other columns. Okay, all other columns are listed over here. So this is my first column vector. Again, I move this first column vector to the right side, and I have a linear equation system, and I get the solution by least square solution. Then AP least square solution is x bottom part transpose, okay, rest transpose x bottom part. This, we have studied this luckily, so I don't even need to think about this. I can immediately apply this one. First column, and there's a minus sign somewhere. Let me put that minus sign over here. Okay. There's a transpose also over here. Is this correct? AX is equal to B. Okay, I think it's correct. So this is Prony's estimate. And how do you find B's? BQ of K's are found as in Pade's method. So there is no change. There is not much change actually. Okay. So only difference is that now I'm applying the least square solution for this bottom part. Very good. So let me see. So in order to understand this a little better, okay, so this is the solution actually. We are done with Prony's method, but I want to understand this Prony's method a little bit better. So I'll be defining the optimization problem, the least square problem, and looking at the equations one more time. So let's examine Prony's approach, i.e. least square solution of bottom part in more detail. Okay. So let me have this. Let's start from this definition. Remember, this is our, let's say, error in, let's say, error in, let's say, modeling. So I'm trying to, given this measurement x, and h is my model for this x, so that becomes the modeling error in modeling. Okay. But if I write this, so this is the beginning of the problem, you may say. So this is x of c minus h of c. Okay. So this is the same error sequence in z domain, isn't it? Okay. But this h of z is bq of z divided by ap of c. Okay, that's my model. Then, as we did before, I multiply both sides by ap of c. Multiply, assume that I can, do such an operation. Assume multiply both sides by ap of c. So actually we have done this before, ap of c in the Pade discussion. So this is ap of c. Let me write x first. X of c, ap of c, minus bq of c. Okay? I get that. Well, now we define this one as Prony's error. Do you remember I was discussing that, this error is difficult to minimize in the, let's say, least square sense, or even it's difficult to equate exactly equal to 0 because I have some nonlinear equations. Okay. But for this one, I managed to at least solve for a's without any nonlinear equation solving, isn't it? So that observation is actually related with this Prony's error definition or Pade's error definition. As we have said, now a's and b, they are separated. And I want this to be equal to 0 polynomial, because it's a polynomial in Z. So I would like to right now equate the coefficients such that this is as close as possible to 0. Okay? Okay, so Prony's error. So let me call this Prony's error over here as, let me write it over here, E of C. Okay, this is our usual error, let's say, Prony's error. So the one with the prime test, modeling error. So this is without the prime, the usual error. And usual error is the Prony's error. Then E of NS, what do I have? As we have written, X of N, convolution, AP of N, minus BQ of N. Okay? This is exactly what we have said before. But let me see, X of N plus X of N minus L minus BQ of N. So I'm writing this convolution, and this is X of N 1 to P AP of L X N minus L. So this is for N 0 to Q, and this is for N greater than Q. Actually, there is nothing new over here. So let's explain. So error is this minus that. Actually, error is what you have on the left side as a vector minus what you have on the right side as a vector. And for n is equal to 0, you have up to Q, you have BQ of Q's, because BQ of Q is still a non-zero quantity, but BQ of Q plus 1 is 0. Okay? Because I have, as you see, Q zeros over here. Okay? Q zeros are allowed in this model. That is this index. So there is nothing new. It's exactly the same equation. So the equation system that you see over here and this error definition, they're identical. There are no differences. I want to equate this one to 0, the bottom part. So the bottom part is n greater than q. Let's say it's q plus 1. So this is the convolution of q plus first sample, x of n convolved with this. X of n convolved with this. Okay? So it's exactly the same. Now, so let's define this least square problem. Let me erase this part also. And let's be careful not to erase this. So, what is the least square problem? Let me see. So let me define an error. So this is for Prony. Let's say Prony. This is a function of a's. Okay? So I will define as n is equal to q plus 1 to up to infinity e of n magnitude square. Okay? So as you see, nothing different. Now I'm looking at this error sequence for n greater than q, this part only. So it's the bottom part of this matrix. And I am evaluating the least square error. Okay. So what should I do? Now I'm taking the derivative, let's say, of this with respect to AP of k, kth one, where k is equal to, an integer between 1 and p. Okay. Because, I have those unknowns. I have p unknowns over here. Well, let's make a change. Let's assume that this can be a complex valued coefficient. So if you are optimizing a real valued function such as this one, but this function is a function of complex variables, we can discuss this further later on, but let's say that I am taking the derivative with respect to the conjugate of this. I will probably explain this a little bit later, but let's do not distract our focus. So this is the conjugate of this. So I will explain. Then you have derivative of j, AP of k, conjugate. Okay. So this is AP of k. So what do I mean by conjugate over here? Now I'm writing this one is also as follows. Okay, E of n conjugate. Now, this means the following. I am treating AP of k and AP of k conjugate as independent variables. Okay, of course you can object to this, but I'll explain this a little further. AP of k has a real part and imaginary part, let's say. Maybe AP of k is 1 plus j. Then its real part is 1, its imaginary part is 1. Its conjugate is 1 minus j. So you may think that AP of k has 2 degrees of freedom, okay? The real part and the imaginary part. So I can always, define 2 variables to define AP of k, real part and the imaginary part. Or you can define 2 other variables, the variable and its conjugate. So for example, if you add these 2, you get the real part times 2. If you subtract those 2, you get the imaginary part times 2. Okay? So you see that if this variable is complex valued, maybe it makes sense to define this conjugate variable as an independent variable. Okay? So we can discuss that later on, but for our purposes, let's accept this result and let's try to evaluate this derivative. Okay? So what is E of n? E of n is over here. But I'm taking derivative with respect to the AP conjugate. Well, there's AP over here, but there are no conjugates. So it's all, not affecting this. So what I have is the following actually. So this is just like a constant, okay, for a given n. So it goes out of this differentiation because it does not contain this variable. Then I have this. So how about this one? Now take the conjugate of this error, this part. I'm talking about this bottom part. Okay, this part. So if you take its conjugate, okay, conjugates over here, and if you take the derivative with respect to AP of k, okay, so what do you have? Well, you have x of n minus k with a conjugate, sorry, not over here. You have this one as x conjugate n minus k, because you have conjugates, and I'm taking derivative with respect to the kth one. K is somewhere in the summation index, okay, so it's L is equal to k, let's say, then this becomes n minus k, okay. So if I do that, okay, I'm almost done. Now let me insert a definition of this. So this is E of n. I'm writing this part. X of n plus L 1 to P AP of L x n minus L. So this E of n. X conjugate n minus k. Okay? Now, of course, well, okay. Let me process this a little bit more. So this is then equal to, well, let me write this, Rx k, 0 plus 1 to P Rx k, L AP of L. So what's going on, where I need to define this, Rx k, L is equal to So this is our definition for this calculation. So what's going on? Now, x conjugate n minus k is multiplying this xn, and I have this summation. So I'm calling that sum at the end rxk0. Let's see whether it matches. When L is equal to 0 over here, well, I have x of n, this thing, multiplied by x of n minus k. Indeed, it is the case. So about this one, now again I have a similar multiplication. Only difference is this is not x of n but xn minus L. Okay. Let's interchange, let's move this inner summation out. So this L1 to P. So of course move this AP of L with the summation to the outside. Move this one to the inside. Now you have xn minus L, x conjugate n minus k. And this is what we call rxkl, okay, over here. If you evaluate that summation, you get that. So this is what we call, again, deterministic autocorrelation. Okay? Because I'm a given sequence. Actually, there is nothing random over here. X of n is our observed sequence. I am trying to find poles and zeros of a transfer function, you may say. And there's nothing random, but this is, again, an autocorrelation, as you see. But its summation index is starting from q plus 1 because of this problem definition, and so on. Okay. Very good. Well, what else? Then, if I do this, okay, okay, but I should maybe explain it a little better. Then, so what was this result? This is the derivative of J, Prony, isn't it? With respect to AP conjugate K. And that is it. So if I equate these derivatives to 0, then calculating derivative of J Prony with respect to AP of K conjugate for K, let's say 1, to P, okay? And equating them to 0. Equating to 0. We get, let me keep this. So I'm equating, for example, this one is equal to 0 for k is equal to 1. Then I repeat the same thing for k is equal to 2, and so on. Okay, so this is for generic k. Repeat the same thing. When k is equal to 1, I have rx 1, 0, but with a minus sign over here. Okay. Then this is rx. This is 1, 1. Rx 1, 2. Rx 1, p. And this goes up to rx. This is p, 1. Rx p, 2, Rx p, p. Okay, so this is Rx p and 0. So this is for k is equal to 1. This is for k is equal to p, and so on. Okay. Let me write one more row. Rx 2, 1. You insert k is equal to 2, 0. That's over here on the right side. Then I have k is equal to 2, 1, up to 2p. Okay? That is the end. Well, this is the equation system. But can we convince ourselves that, this is the same equation system that I will get by, do you remember? I have written this least square solution even immediately. It was x bottom, as far as I remember, rest. This is transpose x bottom rest x bottom rest of this transpose times I have x bottom first column, I guess. 1. There was a minus sign also somewhere. Okay. So do you agree that this is this? For example, if I take the inverse of this matrix, do I get this matrix? So how can I see this? Well, this is, as we have said, the first column. Okay. The rest of these are the matrix that we call x bottom rest of those columns. For example, what is Rx11 in this one? Rx11 is nothing but, okay, Rx11. If I put k and l is equal to 1, so this starts from, so this becomes x magnitude square of the same sequence. It starts from q plus 1. So it starts from x of q, takes the magnitude square of x of q, and it sums the rest. Okay? So it is this vector, inner product with itself, summed up, or inner product of this vector with itself. I mean, inner product is already containing that summation. Okay? That is R11 over here. R12, well, this is this. You know, 1, 2 is one of these vectors is just shifted version of each other. Okay? So it starts from this, you know, x of q again, but the other one is shifted version of it. So you can convince yourself that Rx12 is nothing but the inner product of this column, because I'm talking about this rest matrix, and the next one. Okay? So indeed, this operation, x bottom rest transpose, x bottom rest, this matrix, before this inverse calculation, is identical to this matrix. Okay? That is the way. So there are different ways of getting the same result, but what we see is over here we get something like an autocorrelation like sequence over here also. So that is the important part for our purposes. Okay, so from this point on we will continue shortly.